look at equilibrium is by looking at how soluble are salts. So the dissolution of a salt is a reversible process whose extent can be described by what's called KSP, or the solubility product constant. So just like our other Ks, KSP is a equilibrium constant, but it's specifically for dissolving salts. So when solids dissolve to form aqueous solutions, we assume, for ionic solids especially, that they completely dissociate into separated hydrated cations and anions. Remember that in Chem 1 we watched a video that the ions become surrounded by water molecules, and that's what it means by being hydrated, that they are surrounded by water molecules and they can't go back together anymore. So an example we have is calcium fluoride solid. So the arrow with the H2O just means that it's being added to water, and when it's dissolved, it'll break into its two ions, the calcium ion, and then for balancing purposes, two fluoride ions. Okay? So then, as if we initially start with 0 ions and only the solid, then of course the forward reaction will take place. But then as we increase the concentrations of our two ions, then it's more likely that these ions will collide and reform the solid phase. So this right here is the reverse reaction for where the two products from the original reaction go back to the reactant. And so since we have this reverse reaction possible, then we can get into that state of dynamic equilibrium. Now, remember that the equilibrium arrow is the half arrow like that. I don't have access to one of those in the special characters, so that's why I use that arrow, but that's what it means. So whenever we reach dynamic equilibrium, that means that no more solid can dissolve. So we say that the solution is then saturated. So saturation is different for every single substance, and it's at a different molarity sometimes depending on conditions. But when we do reach equilibrium, then we can create an equilibrium expression. So remember that we don't include solids in our expressions. So if we're looking at this reaction right here, then we're only using the two products in the KSP expression, the equilibrium expression, because the solid never is included. Okay, and so it's almost like a simplified K expression. You'll never have a denominator, which is kind of nice. You're only doing the numerator for when you solve. So that KSP, called the solubility product constant, or simply the solubility product, is used for the solubility of solids into aqueous solutions. And remember that we don't include the solids, like I just said. So now, what's the difference between a KSP and solubility in general? So the solubility product is the equilibrium constant, okay? And it only has one value for every given temperature. So it could change, and that's why you're going to be given temperatures in problems, okay? But just like any other K expression, any other equilibrium constant, there's no unit for KSP. All right? Now, solubility is an equilibrium position. So in pure water, at a specific temperature, a given salt has a particular solubility. So the solubility will have a unit of moles per liter, or molarity. And so that would be the concentration of the ions, okay? So that's the concentration of your ions. I'm just going to say concentration of the ions. Now, it's all relative. So when we solve for solubility, we're going to see that in example 14. We have to think about it a little bit like when we did ice charts. So we'll get there when we get there. But on table 16.1 in your notes and on page 761 in your textbook, I put it on page 10 in your note packet, lists a bunch of KSP values at 25 degrees Celsius for many common ionic solids. And the reason why they're here is because you might need them for the homework problems or just in general what they are. They will be given to you. You won't have to memorize them. but they are there for you. Okay, so now example 13. Let's just learn how to solve for KSP. Okay, so copper 1 bromide has a measured solubility of 2.0 times 10 to the negative 4th moles per liter at 25 degrees Celsius. So calculate its KSP value. Okay, well, first of all, it's good to know the ratio of our ions. So copper 1, we don't see this very often, but copper 1 means that copper has a +1 charge, and bromide has a -1. So our solid is CuBr, and that will break up into Cu +1 aqueous and Br -1 aqueous. And it's already balanced in equation because the +1 -1 charges. Okay, so then if we think about this now the ice chart way, and I'm going to show you on the next one how you don't have to think about it this much. But so if we think initially, we've got something. Like this isn't even included because it's a solid, but we don't have any of our aqueous, which is actually important. Then remember the change, we always add x to the zeros, to the zero side, and you multiply x by the coefficient. Well, in this case, we don't have any coefficients, so it's just plus x plus x. So then at equilibrium, the concentration of the copper and the concentration of the bromide ions is both going to be x. Okay, well, when it tells us that it has a measured solubility of 2.0 times 10 to the negative 4, that is what we plug in for x into our KSP equation. Okay, so it's telling us already what x is. We don't have to do any complicated quadratic formulas or anything like that for it. So now we're just going to plug in. So the KSP is the concentration of the copper times the concentration of the bromide. And so all that's going to be is the 2 times 10 to the negative 4 times 2 times 10 to the negative 4. So the answer is 4.0 for significant figures times 10 to the negative 8. Now there's no unit on KSP, remember, it's just a K value, it's like constant, and that would give you the KSP value for copper bromide. And it's not listed on our table, so we couldn't check it there if we wanted to. Okay, so that would be how you would solve for the KSP. Now, if it's just like a 1-to-1 ratio, you don't have to do all this work, okay? You can just jump right ahead over to here and just think about this as x and think about that as x and plug in the number and do that. That's all great, okay? Well, when it's not just a 1-to-1 ratio, it gets a little bit more involved. And if you like using the ice chart, continue to use the ice chart, but if you can do it without it, that's fine too. So this time, we know that the KSP value for copper 2 iodate is 1.4 times 10 to the negative 7 at 25 degrees Celsius. So we want to calculate its solubility at 25 degrees Celsius. Now, iodate is a polyatomic ion that we did not have to memorize in Chem 1 because we already had 1e6 to measure, or to memorize, so just took it off the list for you. But this is just an example of what you might see in a problem for the AP exam. So, copper 2 iodate, let's look at its equation. Now, we know copper 2 means that copper has a +2 charge. So, let's do some deductive reasoning here. If copper has a +2 charge and there's a subscript of 2 on the iodate, that means that the iodate will have a -1 charge. And since there's 2 of them, to make sure it's balanced, we're going to put a big coefficient of 2 in front of that iodate. Okay? Now, so this time we're given that this is the KSP. Okay? So that will not get plugged into our ice chart at all, but we can still use the ice chart to figure out what do we plug in for the concentrations at equilibrium. Well, initially, remember, we don't care about the solid, but initially we won't have anything dissolved, so both the concentrations and the ions will be 0. So then for the change, we're going to add X to both of them, but for the iodate's purposes, that has that 2, so it has to be adding 2X, actually. So then at equilibrium, X for copper ion, and 2X is the concentration of the iodate ion. Okay, so then now, when we plug into our KSP, the KSP is going to be copper ion times the iodate squared. Because remember that we have to put the coefficient as the power, as the exponent. Okay, so when we plug it in, these two spots right here, it's going to end up being 1.4 times 10 to the negative 7 is equal to X for copper times 2X quantity squared. Okay, so we are plugging in the 2X from right here into our expression right there, and we still have the square because that is supposed to be included for the K expression. Okay, so then when you simplify that out, it'll be 1.4 times 10 to the negative 7 is equal to 4x cubed. And then when you solve for x, then that is 3.3 times 10 to the negative 3. And now, since we are solving for a solubility, it does need to have a unit. You have to solve for something in the brackets or for an x, then you're solving for concentration. So you could put moles per liter or molar. Okay, now since it's just asking for solubility in general, we are done with this. If it were to ask specifically for the concentration of the iodate at equilibrium, then we would have to plug it back into here and solve for that. But since it doesn't ask for it, we don't need to solve for that right now. So a salt's KSP value gives us information about its solubility, but we have to be very careful when using the KSP to predict relative solubilities for groups of salts. There's two cases to be aware of. The first case is when the ions, the same number of ions are produced by all of the compounds involved. So for all of these three compounds, the ratio of the charges makes it so that you have one of each, okay? Right, so like the silver iodide, we have one silver and we have one iodide. And then copper, one iodide, we have one copper and one iodide. And the calcium sulfate, it's a +2 -2, but there's still only one of each ion. So this is what it means when it's producing the same number of ions. So when it dissolves, there are two ions involved. Doesn't matter their charge, doesn't matter how big they are, it just produces the same number of ions. Okay? And so when you do that, when they do have all that same number of ions, then the way that you can compare the KSP values is by knowing that the largest KSP means that that has the largest solubility, or that is the most soluble. So for this list here, remember when we are looking at what is largest, we look at the exponents on the times 10, and the closer to 0 you get, the bigger it is. So, and from this list, the calcium sulfate is the most soluble because its KSP is the biggest. So this is one option that maybe you don't need to actually solve for the solubility, but if you're just given some information about KSP values and you notice that they all have the same number of produced ions, you could compare it that way. So that's one case. Another case is when if you have different numbers of ions produced, then you will actually have to solve for the solubility. So just like we did in example 14, you will have to solve for the solubility first before you can compare. So in this table, 16.2, the KSP values are here given, but like the CUS has just 2 ions, because like that, but then the Ag2S, the silver sulfide, has 2 silvers and then 1 sulfide, and then the bismuth sulfide has a total of 5, because you'll have 2 Bi's and then 3 S's. So when you don't produce the same number of ions, then you have to do the math, like we did in example 14, and solve for X, solve for that solubility. And so then once you have calculated your solubility, then you can compare to see which is most soluble. And again, since this one is the one that's closest to 0, it's the biggest, the bismuth sulfide is the most soluble option from this list. So when you are comparing your KSP values or trying to figure out which is most soluble, these are 2 ways to do it. One, if they have the same number of ions, it's a lot less work. But if they produce different number of ions too, then you actually have to do the math before you can decide what is most soluble. Now, remember that relative solubilities can be predicted by comparing their KSP values only for salts that produce the same total number of ions. Option number 1. Okay, now last but not least, solubility rules can be quantitatively related to KSPs. If you have a KSP value greater than 1, those salts are soluble, so the forward reaction will proceed. Now, if you look back on page 10 at 16.1 table, there are no solubility KSPs listed that are greater than 1. So usually that means that if the forward reaction is going to proceed, that means that those are the ions that are always aqueous. You know, like, and you can look back in Unit 4 for the whole list, but or page 126 in your textbook, but that would be like the sodium ions and the potassium ions and the nitrates and the ammoniums. So those ions, those compounds that contain those ions are very soluble, so that means they won't have a KSP, basically, because we already know that they won't be at equilibrium, where some is dissolved and some isn't. They will always just fully dissolve. Okay, so the forward reaction just goes all the way. KSP can only be for solids or salts that are moderately or slightly soluble. So you can only have an equilibrium when not all of the solid will break up. And so that's a quantitative way to notice that connection to Unit 4.